Thank you very much, Maria, for this great introduction. So you actually summarized my lecture very well, and I feel we can just start right away. But before, I want to say hello to everybody. A little earlier, we discussed already how nice it would have been to meet all in Florence and enjoy the surroundings and enjoy all the time together outside of the lectures. So this part will be missing to a large extent, and I'm very sorry about that. But I hope more so, because we don't have much opportunity to interact otherwise, I hope that you will be awake and active during the lectures and bombard me with questions. Otherwise, it's getting pretty lonely and boring on my end here. And during my talk and during the lectures, I will have an eye on the chat as well. So if you don't feel ready to just jump in and raise your hand and ask something in person, please use the chat. So I'll have a look at that and respond to questions that come up here. And really, I encourage you to interact, because it is a little bit of a synthetic and remote format, but we all will try our best to make the most out of this. Now I'll just start to share my screen, and my lecture will be mainly based on transparencies, and whenever necessary, I can jump out and write something live for you. So don't be scared. I can switch to a little blackboard, and we can have any kind of detailed discussions, little derivations I will do on this blackboard in any case, but also for the discussions, I'll try to use that whenever there are questions coming up. So as Maria already mentioned, it's about ab initio calculations in nuclear structure. And I have to start with a disclaimer, because this is a very wide and diverse field nowadays. And even though I have 4 lectures, I will not be able to cover everything. And in the very end of the lectures, I will kind of summarize all those things, all those aspects of this problem and all the activities that I didn't cover. But you will see pretty soon that I'm going to focus on methods that are using some kind of basis representation to make this Schrödinger equation in most general terms for our nucleus for the many-body problem tractable. So I leave out a few methods and categories of methods which are not using this basis aspect, and we'll come back to that in the very end of the lecture. So my plan for this week is something like that, and I have to say from the beginning, I'm not quite sure about the timing, so things might shift around between the different lectures, but we will have 4 lectures from now to Friday, and we'll have an extra special session, which I would like to use for a little computation for those of you that are interested. So if somebody is not muted,
no, Andrea, I think you
then please mute yourself. Okay, so we will start in a very kind of logical and bottom-up fashion to unravel all the problems that are behind an ab initio description of nuclei. And my first lecture is entitled simply Hamiltonian. So we will discuss the basic setup of the problem, the basic formulation of the many-body Schrödinger equation that we are going to handle. And I'll kind of assume that you have some, of course, knowledge of quantum mechanics, but I'll go through some of the important pieces of many-body quantum mechanics in a very compressed summary, just to fix notation essentially, because there are many options to write different things, and you will immediately see a difference from the typical notation that Gianluca used this morning in that part. So I think it's important just to go through that once again. For most of you, it will be an absolute reminder to good old days of your lectures at university, but I think it's helpful nonetheless just to have a common language. Then we'll discuss the nuclear Hamiltonian, so one of the key ingredients for our many-body Schrödinger equation. And as you know, this is a problem in itself, and this would be a lecture series for a whole week in itself. So I have to be very brief here, but I want to touch upon the most important aspects which make all these ab initio methods that we are using nowadays actually work, and which makes the whole field and this whole endeavor ever so more worthwhile pursuing, because of the important developments regarding our knowledge on the interaction and also our modeling of this nuclear interaction. Then we will talk matrix elements. And this is really a geeky subsection, if you like. You hardly ever see any of this stuff being discussed in talks or lectures. But nevertheless, it is at the heart of any of these many-body methods that I'm going to discuss. Usually this is something everybody suffers with, but nobody talks about it. I will at least give you a little glimpse about why this is something we suffer with and why this is a complicated step in the whole process. Then we'll discuss the two-body problem, something you've seen before, that is the deuteron for us. And I will do it in a way that really blends over to the ab initio methods that we are going to discuss later. And then we'll discuss an important concept and an important problem in itself, namely correlations, and how we can deal with correlations in nuclear many-body wave functions. And this is a kind of advent of the use of unitary transformations, which will play a huge role in the rest of the lectures. Then tomorrow, after having set the stage with the many-body with the many-body aspects of quantum mechanics and the Hamiltonian, we'll start to attack actual nuclei. And we start with light nuclei and the kind of zoo of basis expansion methods that is suited for the treatment of light nuclei. In addition, we will discuss a very important concept, the so-called similarity renormalization group, which is something that plays a major role in all of the ab initio efforts that I'm going to discuss, and it comes in at different levels of the calculation, and it's a very elegant and neat and simple idea. And we'll then go to the first category of methods, namely configuration interaction type methods. That means, in simple terms, diagonalize a huge matrix. So go from your Schrödinger equation to a matrix representation and solve the matrix eigenvalue problem. And that's nothing else but the no-co-shell model in a more general point of view. And I'll also, if time permits, talk a little bit about basis optimization in that context. Then the next lecture on Wednesday, we will venture out to heavier systems, what we typically call medium mass nuclei. So if you are from an experimental background in nuclear physics, medium mass might be something like 100 nucleons for you. For us, this starts essentially with oxygen isotopes and beyond. So we are quite light medium mass, if you like. But you will see that we already need a new kind of pool of methods to tackle these problems. This is where methods like coupled cluster theory and the medium similarity renormalization group will come in. And maybe we'll also discuss a little bit of perturbation theory, because all of them have a very common background, and they have a very common kind of computational pattern to them. And this is what we use nowadays to go beyond this realm of light nuclei. And then on Wednesday, we'll also have this extra session in the afternoon. And I want to use that to kind of try something like a do-it-yourself no-co-shell model with you. So I'll say more on that probably in the lecture tomorrow. You should just be prepared to do something yourself, because this is kind of the best way to learn where the pitfalls and the difficulties with these methods are. And if we manage to do that, then you'll have a full-fledged no-co-shell model calculation, at least for the 3-nucleon system. You'll have seen how this similarity RG evolution works and how to numerically treat eigenvalue problems of large sparse matrices. And then finally, the last lecture on Friday, that will be on precision, uncertainties, and applications. And this is kind of coming to the level of questions that are relevant for research today. Namely, we are more and more dealing with questions of how precise are our calculations and how can we improve precision. And in order to quantify precision, you have to know what the uncertainties of your methods are. And all of this is debated very actively nowadays. And I want to spend the last lecture on some aspects of these kind of most recent developments. Okay, so this is the plan for the week. A lot of ground to cover. And please remember, whenever something is unclear, interrupt me, hack something into the chat so that we can talk about that right away. Good. Let's start with a little bit of warm up, a little bit of background. First of all, I think it's good to be aware in which theoretical context the nucleus and the nuclear many-body problem is situated. So the nucleus is only kind of the upper end of a level of a range or a ladder of very, very complicated system. And it's essentially kind of a hadronic system, namely the problem of the nucleon itself on steroids, because you've clumped many of these hadrons together in a big nucleus. So from the beginning, you might ask yourself, if I deal with the theoretical description of this nucleus, do I have to consider something like the structure of hadrons that form this nucleus? Or at what level does the structure of hadrons and eventually all the quantum chromodynamics that determines how a hadron works, do I have to take that into account if I deal with the nucleus? And if so, or at which place do these effects enter? And this is something which is kind of taken seriously today. And we will not deal with the nucleus at the level of a multi-quark system, as you might want to do it for a hadron itself. But you will see at each and every corner of the problem reminders of the complexity of the structure of hadrons themselves. And you will see that mainly through what we call the nuclear interaction. So as soon as you start putting two or more hadrons close to each other, the interaction of these individual hadrons is super complicated by the fact that these hadrons have substructure and a very complicated substructure, and they are QCD objects, if you like, themselves. So one of the kind of important steps conceptually for us is, how do we go from this complicated world of QCD, which determines how a hadron looks like, to our ab initio description of nuclei? And this will be part of the big trouble and the big complications that you find when you want to describe the nuclear interaction. And we will come back to this point. Now, the systems that we are going to describe, our playground, that's in principle the full nuclear chart. So it's all the way from the lightest systems up to the ends of stability at the heavy end. And I here picked a version of the nuclear chart that also includes this third dimension, the strangeness direction, with hypernuclei, single strangeness hypernuclei here on the first floor. And in principle, this is all our audience. This is what we want to describe. And obviously, it's a tall order to describe them all. And as you will see, and as you've seen in the lineup of my lectures, we'll kind of work our way up in terms of mass number. So we'll start very light and then go up in mass up to, well, yeah, say around here. And the upper end is still a huge problem for ab initio methods. And from my point of view, it will be for quite some time. And you will find the reasons throughout the lectures why it's getting really, really tricky to aim at these heavier systems with the methods we are going to discuss. But the thing is, for us, there's not much of a difference whether we stick to the ordinary nuclei made of protons and neutrons, or whether we also add some extra hadrons, hyperons, for example, to go into the third dimension. So from the methods point of view, we can transfer the methods that I'm going to describe very easily to these other systems. So therefore, I include this dimension. Well, and this slide is entitled The Problem. Well, the problem is simply the Schrödinger equation. And when I say Schrödinger equation, I have this representation independent eigenvalue relation in mind with our Hamiltonian here, eigenstates, and I will use Dirac-Braket notation throughout. So this is not a wave function, that's an eigenstate, a vector of a Hilbert space. We can choose a representation later. We can go to many-body wave functions if we like, or some other basis representation. But for the moment, that doesn't matter. It's just these ket vectors that I'm interested in, and the energy eigenvalues En here. Now, I've simply written down this problem, and having this problem in front of your eyes gives easy access to kind of a definition what this magic label ab initio means. So we want to really solve this nuclear many-body problem. That means this equation based on realistic interactions, which are hidden in the Hamiltonian. And now the difficult part comes, only using controlled and improvable truncations. So that already implies I cannot solve this problem exactly for, say, 16 particle system. I will have to use approximations, but these approximations are of a very special nature. We usually call them truncations because this implies that you can improve on that. You can truncate less and your description gets better, more accurate, closer to the full solution. And this kind of improvability, that's an important ingredient and a defining criterion of ab initio methods. You will always use some kind of approximation somewhere, but you have to be able, if need be, to improve on this to get a more accurate result in a controlled way. And in order to say something about the accuracy of your results, you have to be able to quantify the uncertainties of your theoretical description. And this is the point where we have lots of discussions and lots of new developments over the past 1, 2, 3 years, because this point is only coming to the focus of the community now. Essentially, you could say we have been quite successful with inventing new methods to tackle this problem in this approximate sense. And now we start to worry about ways to really honestly and fully quantify uncertainties in our theoretical description. And this will be something I come back to in the last lecture. Okay, other questions up to that point? So just be reminded, if you want, you can hack something in the chat or raise your hand and just interrupt me, no problem with that. Okay. Now, when I wrote down this equation, I had a number of implicit assumptions already in the back of my mind. This equation is already a very specific kind of perspective on the problem. The first thing, if I think about these many-body states psi n, I'm thinking of states of A nucleons, protons and neutrons. So from the beginning, I decided to use nucleons as effective degrees of freedom, not quarks and gluons. That's a choice. That's a choice that, say, conventional nuclear structure theory uses. But of course, if you are able to deal with quark systems and even more complexity, you can think of a nucleus as a multi-quark system. And people are starting to think along these lines. For us, we will stay to this simplistic, if you like, picture of nucleons as degree of freedom. And as you see from this non-relativistic quantum equation, we use a non-relativistic framework for the description. There are relativistic effects which might be important, and they are present and absorbed, if you like, in the Hamiltonian. So you do the same thing that you do for a non-relativistic description of a hydrogen atom. You have fine structure effects that are relativistic in origin, but you don't have to solve the problem relativistically from the beginning. You just include these effects as corrections in your Hamiltonian. And this is done the same way for nuclei. The interactions that we are going to use have these relativistic corrections built in. And what you also see, of course, we use a Hamiltonian formulation. So we don't start with a quantum field theory or a Lagrangian. It's really conventional many-body quantum mechanics. And the final point, I wrote this discrete counting index n at my energy labels En here. So that means I'm dealing with a discrete part of the spectrum of this Hamiltonian. I'm looking for bound states at the moment. I'm not discussing continuum, so the continuous part of the spectrum with scattering physics, reactions, all of this. This is extremely interesting and important in some instances, but this is another aspect that I'll not touch upon, how to include continuum in these methods, because that just adds a huge level of complexity to the problem. Okay, so these are the things we have to accept whenever we want to talk about a Schrödinger equation that we are trying to solve. Now let's look a little more into the individual parts of this super simplistic equation. And the individual parts are, number one, these many-body states. And you can ask yourselves, what do I have to know in order to say something about the structure and the setup of these many-body states? First of all, we're dealing with many-body quantum mechanics. And many-body quantum mechanics is essentially an upgrade of single particle, simple quantum mechanics, but with additional complications from the fact that the particles that I'm going to describe are identical. Things like antisymmetry of your many-body wave function emerge as additional requirements, and that gives rise to new technologies, something like second quantization, which is very, very handy for many of the calculations that I'm going to show.
Robert, you have a question in the chat. You have a question in the chat, but maybe you'd like to answer now. Because
yes, just let me finish this point. I see it. I will come back to this question after this box. And so we'll have to talk about basis sets for this many-body space, and that will kind of also prompt the question of truncations for the first time. This is one of the truncations that I indicated. And this is essentially what we'll discuss in this little section on many-body quantum mechanics. So there is a question. Pardon for the naive question. There is no naive question. I'm sure it's an excellent question. But does one often need to decide between ab initio and other methods like DFT, or are these complementary? So I think they are absolutely complementary in all possible respects. Often, from my perspective, of course, I'm doing the ab initio stuff, so I would like to do everything ab initio, but I have to tell you, I cannot do many, many, many things that are super important for understanding nuclei, for interpreting experiments. I cannot do that stuff with an ab initio method. Nobody can do that nowadays, and I think for a very long time, there will be lots of questions which simply cannot be addressed within this ab initio spirit. And I'll come to that in more detail later when we try to go to heavier systems. So I would say for the light nuclei, say P shell, something up to the oxygen isotopes, we are in pretty good shape with the ab initio methods. We can do a lot there, and we get a pretty accurate description of systems. You can go heavier. You can go to calcium isotopes. You can go maybe to tin isotopes. But once you are around there in this medium mass regime, you will see that several problems are popping up. It's not so much the problem of the many-body method. You can do that nowadays, but you start to see deficiencies in your Hamiltonian, and you maybe start to see problems with your basic paradigm of setting up the interaction in your Hamiltonian, so that you would kind of more adopt the philosophy of density functional theory, where you always have some imperial input in the construction of your functional. And I think it's complementary, and on the long term, I hope that there will be some kind of merger of the two, so that one has a really transparent interface between the two domains, ab initio and density functional, so that one can switch from one to the other and one knows exactly what that means in terms of accuracy and translation between the two worlds. So I think we will need both for a long, long, long time. And the ideal future would be that the two kind of come together and merge. And there are several efforts along these lines to really bridge between these two kind of languages. Yeah. Okay. Now, this is kind of the simple part. This many-body quantum mechanics. That's textbook stuff, if you like. Once you've captured all the relevant physics here, you can ask yourselves the next question, namely, about this Hamiltonian here. In order to even think about solving the Schrödinger equation, I have to know something very specifically about this Hamiltonian. And that's the point where nuclear forces come in. And this big problem I already mentioned, that we have to work hard to get a suitable model for nuclear forces in the first place. And the kind of approach that nowadays is favored in the ab initio community is to use chiral effective field theory for that purpose. And we'll have to discuss a little bit about that. You will find that immediately you are faced with the need to include three-body interactions into your description. And this is something which 10 years ago was a huge hurdle. We've learned since then, and essentially nowadays there's not a single ab initio calculation which doesn't include three-body forces from the beginning, but it's a price to pay. And you have to ask yourself about the quality of your interaction model itself. There are questions of consistency, convergence, and so on, which really pertain to the way you set up the nuclear interaction. These two things we'll discuss today. The rest of the lecture, the rest of the week, we'll discuss this little equal sign here, if you like. We'll discuss ways to solve this equation, this eigenvalue problem, as it looks like, in an ab initio spirit. So we'll have to discuss correlations and the similarity transformations I mentioned. We will discuss large-scale diagonalization approaches and all this medium mass technology, starting from coupled cluster in medium SRG and so on, that have been developed and established over the past decade or so. So this little equal sign will keep us busy for the rest of the week. Okay, other questions, more questions up to this point? Okay, all still happy? Are you all there still? Maybe just type a little hi, I'm here in the chat that I see I'm not alone. So what I'm going to do now is I'm trying to give a very brief reminder about many-body quantum mechanics. Hey, thank you for the highs. Now I feel better. I'm not alone. That's great. So very quickly, and interrupt me if it's getting too quick. The first thing we have to be aware of is the elementary degrees of freedom in a quantum description of a single constituent particle, a single nucleon. And Gianluca already started with this, but you will see a difference to what Gianluca did, namely, I'm again not using any kind of wave functions to start with. I'm sticking to this ket notation. And my generic notation for a single nucleon state is this ket alpha. And in order to characterize a nucleon, I have to specify the state in kind of coordinate space, position information, momentum information. I have to characterize the spin degree of freedom of the nucleon and the isospin, that means proton or neutron. So essentially, my full single nucleon state is a tensor product. These are the little product signs here with a circle around it. It's a tensor product of a state in a position Hilbert space, spin, isospin. And I can, just for specific, or to be specific in what I'm talking about, I can choose a basis for these different parts of my single nucleon Hilbert space. For example, for this position information, we often use something like a spherical harmonic oscillator basis or any kind of spherical single particle potential. Spherical implies spherical symmetry, and the spherical symmetry at the single particle level implies that you have good quantum numbers of angular momentum. And this is something which we love. Angular momentum quantum numbers is great. And later on, I'm trying to convince you why this is so. You might be appalled by that from the beginning, because as soon as you start with angular momentum, that implies sooner or later you start with angular momentum coupling, like here. And that's something which you might not like, or which might look very complicated to start with, but I'm trying to convince you that this is actually a very efficient way. And if you speak in technical terms, it's a very efficient way of data compression. And we'll come to that later. Therefore, we are going to use symmetries, and rotational symmetry implies angular momentum as much as we can. So typically the basis in position space that we use are something like L and M. So the orbital angular momentum quantum numbers for the squared orbital angular momentum operator and the 3 component of it. And in addition, some kind of radial quantum number, little n, which could be just the radial number of nodes of your wave function, as you know it from all of these kind of one-body spherical symmetric problems. And if you want to be very specific, just think harmonic oscillator, spherical harmonic oscillator in this angular momentum representation. Then there is...
You have a question about that?
Yes, I'll come to that in a second.
Sorry, I don't know. I'm sorry. You see them all then.
Yeah, I see them, no problem.
I don't interrupt you anymore.
So if there are raised hands or so, then you might remind me, because I might not see them, but the questions in the chat I do see. Then there is spin, and spin is just this very simplistic and weird quantum number. The nucleon, proton, and neutron as a particle has the property that the spin S quantum number is always 1/2. You cannot change that, but you can change the orientation of spin or this projection quantum number, which are called MS. And that can be either plus or minus 1/2, spin up or spin down. So this is a very simplistic 2-dimensional little spin Hilbert space that we have to consider. And it's the same for isospin. We use isospin to distinguish proton and neutron. And the question in the chat already refers to that. Isospin in principle is set up very similarly to the spin. You have a quantum number for the isospin squared operator related to its eigenvalue, and that's 1/2. And again, this is the particle property. That's a property of proton and neutron, or the nucleon. And it allows for 2 dynamic states, again, this projection quantum number, which I call MT, which is proton or neutron, or if you like, isospin up, isospin down, but you have to be very careful. Isospin lives in a different coordinate system as spin, so it's not affected by spatial rotations. And that's exactly pointed out in the question. So the isospin degree of freedom that you really have, the thing you can change, is proton or neutron, so this projection quantum number. The isospin T quantum number, that's fixed, like the spin as well, and that's a particle property. And you know, if you look through your Hadron Zoo, there are other guys with different isospin quantum numbers that form the multiplets. So it's the same for spin and isospin. It's kind of a mixed bag. The first part is fixed, and the projection is something you have to consider as a dynamical degree of freedom. And in our everyday language, and therefore this question is just spot on, we don't distinguish that. You say something about the spin state of a system or the isospin, You have to be careful what you really mean by that. It's always these two quantum numbers, T, MT, S, MS, and only one of them something you can change. Now, I mentioned once you have angular momenta in the game, like this orbital angular momentum L or the spin S, you're tempted to start to couple angular momenta for a good reason. Things become efficient, again, from the point of view of symmetry. And some simple thing that you've surely seen in your lectures is spin-orbit coupling. So you take the orbital angular momentum L and the spin, and you couple that to a new total angular momentum for the single nucleon that you call little j, and a corresponding projection quantum number m. And this coupling is just expressed in terms of a series of coefficients, Clebsch-Gordon coefficients, and you sum over all the m components of spin and orbital angular momentum to get to this new structure. I only mention that because later you often see this kind of notation with this cat with a list of quantum numbers in there and these brackets. And whenever there are brackets, this implies angular momentum coupling. The two angular momenta, L and S, which is always 1/2, are coupled to J and M. And you will see more complicated notations like that, where you have multiple nested brackets for more complicated coupling schemes. And as I said, I promise I will convince you that this is something good. It's scary, but it's useful. Okay, now this is the single nucleon. If we go to multiple nucleons, so A nucleons, then we first have to face the complication of many-body quantum mechanics that we are dealing with systems of identical particles. In these situations, we know that the many-body states which can describe our system have to fulfill a very specific symmetry requirement under transpositions. So reordering of the single particle states in your imagined list of A single particle labels. And there are two classes, two kinds of allowed states, those which are symmetric under exchange of two single particle labels. And this exchange in a more posh way can be expressed as transposition, described by this transposition operator Ti, which just swaps single particle label E, I, and J. And if your state is reproduced under such a swap, so just is the same with an +1 prefactor, which is nothing, then you talk about symmetric states. If such a transposition induces a minus sign, so it gives you the same state, but with the opposite direction, if you like, then it's an antisymmetric state. And this is important, and this is a major complication when you deal with nuclei as many particle systems, because it implies immediately that something like a simple product state, so the same construction that we use to glue together position, spin, isospin, now transferred to gluing together individual single particle states, alpha 1, alpha 2, up to alpha A, with these tensor products. This structure is something we call a product state, but this is not allowed for any of these systems of identical particles, because I need either the plus for symmetric, and for us, for the nucleons, the minus sign whenever I transpose two single particle states. If I do this transposition thing here, for example, with the first two states, alpha 1, alpha 2, so I apply a transposition operator T12 here, it will swap these two guys, and the resulting product state will be orthogonal to the original one. It's neither plus or minus, it's simply different. So you don't have this critical property. And this is why we have to work a little harder. If we could work with these simple product states, life would be so much easier. But it isn't. We have to consider this symmetry requirement, and we know that for our nucleons, because they are half integer particles, the spin statistics theorem tells us that we have to use antisymmetric states. So whenever in the following I write a many-body state, it's always an antisymmetric state. I will never come back to these product states. If I need one for a moment, I will write them explicitly in this form. But whenever I write a simple cat with lots of single particle labels in there, then this means antisymmetric state. That's important. Now, how do I get these antisymmetric states? They seem to be a bit tricky with these minus signs popping up whenever you swap two single particle labels. Well, the easiest way from a formalistic point of view is to start from your product states, which are not antisymmetric, and make them antisymmetric by hand, if you like. And you can do that by a simple trick. You cannot work with a single product state, but you can take all possible rearrangements of the single particle labels in your product state here. And applying a rearrangement of labels, this is something I can do via an operator, the permutation operator. That's just a transposition on steroids. Again, you do many transpositions to rearrange things such that you have it in a different order, and this different order is characterized by mathematically a permutation pi. So simply a reordering of your index set 1 to A to some different order. And this operator P is exactly doing this job for you. And then you sum over all possible permutations. So you take all possible reorderings combinatorically of your A single particle states. And then the tricky part is you add the minus signs that you need. So whenever a permutation requires an extra swap of two particles, so an extra transposition, then you add an extra minus sign. And this is captured by the signum of the permutation, which is just -1 to the power of number of transpositions that you need to do in order to describe this permutation. And then you end up with this huge sum over A factorial different permutations of different product states. So this gives you an explicitly antisymmetrized state. And if you remember your math lectures, this thing here, which I call antisymmetrization operator, has exactly the formal structure of a most general determinant. I don't need a determinant yet, but this already tells you that this is exactly what you call a Slater determinant. It's an antisymmetrized product state. And you don't need to go to position representation to write it down. This is kind of the nasty cat notation thingy for that. But it's just the same physics, and it's the same object if you go into the wave function picture in the end. Now you see a simple many-body state like this one already has hidden inside these huge sums over permutations, funny signs, permutation operators. So it's very complicated. And if you now start to compute something like an expectation value or matrix elements with such a many-body state, you will suffer from these summations and the permutations. That's a huge mess, very tricky stuff. But this is the price to pay for the fact that we are dealing with a system of identical particles. And you know very well that this antisymmetrization procedure has an immediate consequence, which is important physics, namely the Pauli principle. Because whenever you try to antisymmetrize in that way, a product state where two single particle states are the same, you will end up with 0. Because you can work that out if you like as an exercise for a 3-particle system, and you write down all the different permutations of 3 single particle states, you will always find in this list, which is sum up, pairs of states, which, if all of them are different, simply are distinguished by a swap of, for example, these first 2 guys, alpha 1, alpha 2. But if alpha 1, alpha 2 are now the same, then these 2 states, which differ only by this one swap of these 2, are the same, because the states are the same. However, these 2 states end up with the opposite sign in your huge summation. So pairwise, all of these states will drop out and you will be left with nothing. So this projection, if you like, on antisymmetric states leads you directly to 0, a null vector, nothing. It's not possible. You cannot antisymmetrized a state with two identical single particle states in there. Because your state has to be antisymmetric, in reverse, you can conclude that the Pauli principle holds. It's not allowed to have two particles in the same single particle state. If you're dealing with fermions, that means antisymmetric states. So it's a simple consequence of this. Now, these later determinants are nice because they give immediate access to a basis of your many particle Hilbert space. Because if you take all possible Slater determinants from all possible combinations of single particle states alpha from a complete single particle basis, you're guaranteed to get a complete basis of your anucleon Hilbert space. And this is what we are going to use all the way. So this is kind of the important feature that we gain, or the benefit that we gain through this antisymmetrization procedure. You have a clear strategy for developing a basis in your A-body Hilbert space. You just pick a single particle basis, and then you combine all the different states of the single particle basis in all different subsets. You pick out A of them, all possible A subsets of them, and then you have a basis. This means you can use this basis of Slater determinants, for example, to expand an arbitrary state in your many-body Hilbert space. And this arbitrary state is called psi. And you can expand that simply in terms of a sum of these Slater determinants for all possible combinations of single particle quantum numbers alpha. So this alpha now is kind of a complicated counting index. So it hides all this N, L, S, T, whatever quantum numbers. But I treat it as just a counting index so that you can sum over it. There's one thing you have to be careful about. If you write down this explicit basis representation of your state psi with expansion coefficient C and the Slater determinant cats here, because two Slater determinants that only differ by a swapped pair of indices, they are linearly dependent. They have just the opposite direction, but you can correct for that with a prefactor. So they have the same function in your basis. So you have to be a bit careful not to include all possible arrangements of your indices, but only one set, one kind of sorted set in some sense is enough. And this is this double counting issue that you have. Therefore, you have this funny notation here with the alpha 1, smaller alpha 2, and so on. So I pick them in one specific formal ordering, and I only include one of the orderings in this summation because all the other reorderings would just boil down to nothing or a minus sign in front, so linear dependent vector. I don't want to include that. And this is also visible if you use something like the nice formal tricks of computations and derivations in quantum mechanics. You often use the identity operator to change into a basis representation. You can use the Slater determinant basis to write down a resolution of this identity operator in this specific basis. But again, apart from this cat bra structure, the so-called dyadic product, you have to watch the summations. Either you limit yourself to one specific ordering, or you have to correct for this double counting, which makes this 1 over a factorial factor if you want to work with unrestricted sums here. So this is a teeny little bit that's tricky in practical calculations. I just wanted to mention this. Now, I've said it's pretty, say, confusing to work with these sums over permutations. It would be nice if one could do that in a different way. And one can, and this different way is second quantization. Sounds massive, but it's only a formal trick. It's no new physics, no new quantization. It's just a different formal way of handling these many-body states. The first thing you have to do is a formal thing. You go from a particle Hilbert space to the Fock space, which is just a direct sum of Hilbert spaces of all possible particle numbers. You have to do that because we are in a minute designing operators that change particle numbers. So they promote you from one Hilbert space to the next, for example. So you have to combine these Hilbert spaces into a Fock space, and you include something weird, namely a zero particle Hilbert space H0 here. This is very useful. This space only has a single state. It's one-dimensional, and the single state is the so-called vacuum state. I write it as ket 0. Careful to distinguish it from the null vector. It's not the same, because this ket 0 is neatly normalized. So funny relation. 0 times 0 in the scalar product gives 1. So be careful. This zero vacuum state is not the zero or null vector, but it simply characterizes technically a starting point for us. It characterizes the absence of all particles, the vacuum, therefore it's called vacuum state. For us, this is really just a neat little tool. The physics of this vacuum state is much more profound if you go to quantum field theories, or if you go to symmetry breaking theories, things like that. You often have this concept of a vacuum state there, and it's much more, say, rich in physics in these other fields. For us, it's really pretty simplistic, just a starting point without any particles in there. And if you have that, you can invent a new operator, which we call creation operator, which creates a single extra particle in a specific single particle state alpha, and it simply adds it to your many-body state while automatically guaranteeing that the new state is normalized and antisymmetrized. So all this tricky stuff is done automatically by these creation operators. You can apply this creation operator, which we call a dagger, and this index alpha indicates a single particle state, which is supposed to be generated. You can apply that to the vacuum state, and then you get a simple single particle state alpha. The more interesting stuff happens if you apply it to a Slater determinant, which has a single particle states alpha 1 to alpha a already. Then you end up with an a+1 Slater determinant with this extra single particle state alpha here added in the first slot of your list. This is great. This new state is automatically, again, antisymmetrized, normalized, ready to work with it. But you have to be careful. There is a Pauli principle, and the Pauli principle shows up in this operation. Namely, in principle, you could try to create a single particle state alpha that's already there. That's already in this list. If this is what you do, then this creation operator has to respond with a 0, null vector, nothing. Because there is no antisymmetric state which has two identical single particle states. So here, this distinction, either your state is new, you haven't occupied the state already, then you get the a+1 Slater determinant, otherwise you get 0. In this way, you guarantee the Pauli principle. And that's a little complication you have, but otherwise, it's pretty kind of mechanical and intuitive to work with these creation operators. And of course, you have the opposite. You can destroy particles, annihilate particles by an operator which is simply called A. If you apply that to a A-body Slater determinant, and if your single particle state alpha here matches one of the single particle states that are already present in your Slater determinant, then you will simply remove this single particle state. So you end up with the A-1 Slater determinant, and this index alpha that I assume to be equal to alpha I has been removed here. Again, there are two little complications. Number one, you get this funny prefactor with a minus sign. This is not too surprising because this minus sign is from transpositions, swapping. And by definition, we have to specify at which slot of this list of single particle states the particle has to be annihilated. And by definition, these operators, the creation and the annihilation operator, are always acting on the first slot here. If your state that you want to destroy is at the position I and not the position 1, you have to first bring it to position 1. And that means you have to swap it with A-1 neighbors to the left. And that creates A-1 minus signs, if you like. So this is a -1 to the power A-1. And of course, if you try to destroy something which is not there to begin with, then you get the answer that doesn't work, and that means null vector. Okay, now it's not clear from this discussion why this should be useful. It's a nice game, if you like, but you see the first indication of where the difference is and why this is indeed, for practical computations, a huge relief if you look at the antisymmetry requirements to begin with. Instead of talking about symmetry, antisymmetry for swaps of these single particle states, we can now talk about symmetry or antisymmetry of swaps of operators. So that means it's the behavior of these operators under transpositions or under commutation of this operator products. So therefore, as you know, anti-commutation relations are defining criteria for these fermionic creation and annihilation operators, and they essentially encode this minus sign gymnastics for you. And it's much easier to deal with swapping operators in a product than dealing with all these sums over permutations. And that becomes immediately clear if we go back to our simple Slater determinant. Now I write the Slater determinant with its A single particle indices, alpha 1 to alpha A, as a chain of creation operators with indices alpha 1, alpha 2 to alpha A applied to the vacuum state. So one after the other, I create the single particles states I want to have in my Slater determinant. I start from the last one. Alpha A is put in here. I have a one-body state with alpha A. The next A dagger comes and I get alpha A-1, and so on and so on. And I build up this A body Slater determinant just through the string of creation operators. No normalization, no extras required. That's all taken care of by the formalism itself. And now you see immediately, if I compare this thingy to the same relation with two indices swapped, then I can connect these two relations. On the left-hand side, I know that the state is antisymmetric, so the swap, if I want to reverse it, gives me a minus sign. The same swap in this operator chain means I have to commute two operators, swap their position, and that has to generate a minus sign, the same minus as on the left-hand side, and this is encoded by this anti-commutation relation. Now, this is a way to write a Slater determinant in second quantization. It's not the only way. In this way, we start from nothing, from the vacuum state. Later, in the discussion of our medium math methods, we will use a different picture. We'll not start from the vacuum, but we will start from a Slater determinant that already has all the A particles in there, in one specific single particle state. And we call this specific Slater determinant reference Slater determinant or reference state. Now I can still generate all possible Slater determinants based on this reference state by doing something that we call particle Hall excitations. Again, I use my creation and annihilation operators and just shuffle around the states that are listed in here. I remove states which I don't like and put in new ones that I would like to have. And depending on the number of states I have to remove and put back in, I can sort this into a hierarchy of so-called particle Hall excitations with respect to my initial reference state. If I just replace, so to say, one particle or put one particle from a state alpha A to a new single particle state alpha P, then this is a one particle, one Hall excitation, and I can write it with one annihilation, one creation operator. If I have to reshuffle or move two particles from alpha A, alpha B to two new single particle states, alpha P, alpha Q, then this is a two particle, two Hall excitation, and I need 2 annihilation and 2 creation operators for that, and so on. If you go all the way to a particle, a hole excitations, you can convince yourself that you can describe any Slater determinant of my complete basis through this process of particle hole excitations. So this is something which is very useful later, and we'll discuss this in more detail. I just wanted to point out that second quantization is really the elegant way to combine 2 pictures. You can write the simple Slater determinant starting from vacuum, or you can write this particle hole picture starting from a reference state that already has a specific single particle states occupied. Now, so far we've used second quantization to describe states. That's half of the story. We also need operators, something like the kinetic energy or a 2-body interaction. And here in the left-hand column, I've kind of written my notation for the first quantized form, the standard form of this. If you want to describe the kinetic energy of your a-particle system, then you measure the kinetic energy of each individual particles and sum over all particles. If you want to evaluate the total potential, the total interaction in your a-particle system, then you take all pair interactions between particles I and j and sum over all pairs. So this is okay, this works, you can do that, but again, it's getting tedious sometimes, and you can use the language of second quantization to also describe these operators very elegantly. The kinetic energy can be described as a simple kind of 1 particle, 1 hole type structure, namely 1 annihilation, 1 creation operator. So you annihilate a single particle in a state alpha prime and create it in a state alpha. And you multiply the whole thing, the new state that you get from this particle hole operation, with an amplitude, a prefactor, which is simply the single particle matrix element of your kinetic energy operator with these 2 states alpha prime alpha. And then you sum over all your possible single particle states alpha and alpha prime. So essentially you scan your single particle basis twice with your initial index and the alpha index, and you probe with this particle hole operator, is this occupied, can I replace it? And if I can replace it, then I will add this new state with this amplitude given by the matrix element of the corresponding operator. So you see, essentially, the only thing I need to qualify and to determine an operator is the complete set of matrix elements. Once I have all these numbers, that's a huge table of numbers in a specific basis alpha that I picked. If I have this table, then I can specify how this operator works in my many-body system simply via this creation annihilation operators. And it's the same for a 2-body interaction. Instead of the 2 indices ij, I now have 2 annihilation and 2 creation operators. And I have this 2-particle matrix element of the interaction itself. Again, this is a huge table of numbers for my complete single particle basis states here and here. And once I have this huge table of numbers from whatever source, I can use this operator simply in this second quantization language. And this is actually the way we will work throughout all of the methods I'm going to discuss. It will always be kind of specifying your relevant operators, such like kinetic energy, potential, but also other observables like the radius of a nucleus or some electromagnetic property via sets of matrix elements of the corresponding operator. Once you have a set of matrix elements, you're done. You can start your many-body calculation with that. This is the input that you need. Therefore, this keyword matrix element that I advertised in the beginning is so important for us. If you can write down, compute the matrix elements of an operator of choice, you're ready to use it in your many-body scheme. Okay. Are there questions up to this point? Okay. Everybody's still happy? Good. Then I want to spend just a few minutes on, say, a geeky part. Later, I will do that later after discussing the Hamiltonian. We'll come back to this matrix elements. Keep that in mind. Now we know a little bit about the many-body side of things, many-body quantum mechanics. We can now face a second problem, the Hamiltonian itself. And this will be very brief here. I said this can be a lecture series in itself. And let's first start with a tiny technical thing. The Hamiltonian that we are going to use in our many-body Schrödinger equation, this simple H, that's composed of kinetic energy, T, and various interaction terms. Two-body interaction, which I call V and N here, between any two nucleons. There will be a three-body interaction, V3N, and there might be four-body, five-body interactions, whatever you want. There will be Coulomb interaction as well. For those of you who wonder, that's for me absorbed in this V and N. So we also always have the Coulomb interaction explicitly included here. Now, the interesting point for the moment is not so much the potentials here or the interaction terms. Let's look at the kinetic energy for a second, because here is a very important general thing about nuclei. The only term in this Hamiltonian that is sensitive to the properties and the motion of the nucleus as a whole. For example, the center of mass of the nucleus flying through space after it came out of your secondary beam facility with a giga electron volts of energy. This part is the only thing that is sensitive to the center of mass of the nucleus. And it's only the kinetic energy of the center of mass motion which informs this complete Hamiltonian about the state of motion of the total nucleus. All the rest, that means the remaining part of the intrinsic of the kinetic energy, which we call intrinsic kinetic energy, that's just, so to say, the relative motion of the nucleons with respect to the center of mass of the full nucleus, and the interaction terms, they only see the relative intrinsic degrees of freedom. They see distances between nucleons or relative momenta of nucleons, but they don't care about the motion of the nucleus as a whole. So essentially, your Hamiltonian can be decomposed into the center of mass kinetic energy plus the so-called intrinsic Hamiltonian. And this intrinsic Hamiltonian is the thing we are interested in. That's a non-trivial part. The center of mass motion you can typically describe by a plane wave or something like that, free moving particle, which is a whole nucleus. But the intrinsic part holds all the physics. And if you ask yourself for a moment, if I'm going to describe or going to measure properties of the nucleus, do these properties depend on the state of motion of the nucleus? Is anything that you would look up in some kind of data tables on nuclear properties dependent on the state of motion? No, it isn't. You're interested in intrinsic properties, properties which only result from this part of the problem with intrinsic Hamiltonian, something like binding energy or radius of the nucleus or some excitation spectrum or some electromagnetic transition strengths. All of these are intrinsic properties that only look at the relative state of motion of the nucleons in the nucleus. So in principle, I would like to separate the problem into these two pieces. Center of mass, I don't care about that, and the non-trivial intrinsic part. And if I go for this intrinsic Hamiltonian, that has lots of nice symmetries I can exploit. Of course, by construction, it's invariant under translation, can shift the nucleus around from here to here, and the ground state energy will not change. It's invariant under rotation. I can turn the nucleus in space, nothing happens. Galilei boost, I can kick it from being in rest to being at some low velocity. Binding energy should not change. Parity, time evolution, time reversal, all these nice symmetries have to be fulfilled by this intrinsic Hamiltonian. And that's a powerful guiding principle. These symmetries are important to constrain the nuclear interaction, to constrain all these VNN, V3N terms. And it's also important for our later solution of the many-body problem. In principle, I have to respect these symmetries. And this is something we'll come back to later. So the thing is, the eigenvalue problem I want to solve is for this H intrinsic, not the full H. And I'll only discuss H intrinsic in the following also. If I call it Hamiltonian, I just refer to this intrinsic Hamiltonian. And now the only remaining question is, how can I determine these VNN, V3N, and so on interaction terms? And this is complicated. And this is complicated because of the underlying QCD physics. And to kind of hammer in this point once more, if you look at the nuclear interaction, the interaction between two nucleons, then this is certainly not a fundamental interaction like, say, Coulomb. It is complicated. It's something like a residual force, very analogous to the van der Waals interactions between neutral atoms. So you know, if you have two atoms, they have their electron clouds, they're neutral, each of them. The electron clouds and the structure of these clouds is governed by electromagnetic interactions. And if these two atoms are far apart, they don't care. They will not interact with each other because they are neutral objects, and it doesn't matter that there is another atom. However, if you bring them close to each other, so that the electron clouds start to overlap, then suddenly you resolve the substructure of these complicated beasts, the atoms, and you induce a so-called residual of van der Waals interaction, which is simply due to the reconfiguration of the electron states, due to the fact that you start to see the other electrons. You overlap with density distributions, you have polarization effects. So this van der Waals interaction is electromagnetic in origin, but acts between neutral objects if they are sufficiently close, if they overlap. The same happens in a simplistic picture in your QCD world. Nucleons or hadrons themselves are complicated objects. If you take a hadron, or let's stick to the nucleon itself, then it's a color neutral object. You don't expect direct quark exchange with another nucleon which is somewhere around. Only if you bring them close together, all these quark-gluon distributions will polarize, and you will have an effective residual interaction, simply like the same mechanism as for the van der Waals forces. But now it's rooted in QCD, in the strong interaction, and it's mediated between color neutral objects if they are so close to each other that they essentially touch and see each other. And here on the left in this cartoon, you see two nucleons with their simplistic, oversimplified quark content and this cloud of gluons and additional quark antiquarks, and a typical scale. So you know the typical radius of a nucleon is 0.5 Fermi, so the diameter is 1.6 Fermi. Or if you bring them close to each other so that they touch, and that's very simplified, you have a distance between the centers of 1.6 Fermi. So at that distance, you can be sure that your simple picture of color neutral objects is not true anymore. If you compare that to the average distance of nucleons in a nucleus, so you just take the typical nuclear matter density to the -1/3 power to get a length scale, you end up with 1.8. So that means in a nucleus, nucleons actually sit in close packing, and they sit all in the range where you have these polarization effects and these induced interactions. So it is this very complicated.
Sorry for interruption. May I record the rest of this lecture? Our building is going to be closed and I have to leave.
Okay.
So
I think it is recorded in any case. So I think you don't have to worry.
Yes. May you enable my recording?
No, I'm saying that it is recorded in any case by the organizer.
Yes,
So
yes, I understand. But in this part of the world, we have no easy access to the YouTube.
Oh, okay, sorry. Good point. I don't know whether
Yes.
it's fine with me. I don't know whether I can do that or whether the organizers have to do that. So
I have asked the organizers, but I have received no reply so far.
Okay. Okay.
So can you do it for me? Enable
I'll
just.
try. I'll allow
Yes.
to record local files. I don't know whether this is the thing.
会干群.
Yeah. So.
Yes. Yes.
So does it work?
Okay. Okay. Yes, I can record now. It's
okay,
recorded. It's being recorded now. Thank you.
Okay.
Thank you.
Good. You're welcome. Okay. Now the thing is, we have to face with this complicated situation, and you will inherit all these complications of QCD in your nuclear interaction. So this is difficult, and for a long time, for this reason, we were not able to really make a direct connection to QCD physics for the construction of our nuclear interaction. And what I call yesterday is not so far away. So it's just in the mid-2000s that we started to change there. But for a long time, also in ab initio theory, we were using what nowadays is called a phenomenological nuclear-nucleon interaction. Phenomenological is now really different from the phenomenology that you would discuss in a mean field approach in a density functional theory. So this is not something like a Skirm or a Oni interaction, for example. It's still a realistic force which describes few body physics, phase shifts very, very accurately. But we call it phenomenological nowadays because it lacks this connection to QCD. And there are famous examples for these interactions which are still valuable for comparison and for some calculations nowadays. That's, for example, this famous argon family of interactions, the argon V18, or there's a similar one which is more rooted in the meson exchange picture. So it has kind of information from QCD in there, which is the CD bond. They are essentially terribly complicated parameterizations of a potential, which respects all the symmetries I've mentioned earlier, but the rest is essentially fixed by fitting to data. And I will just show the typical example, the argon V18 potential, because this is really useful to understand some of the physics of this nuclear force. I will not be able to show these pictures later on, and I'll discuss why. But the argon potential is what we call a local interaction. It can be written as these conventional functions V of R, so strength of the potential as function of distance of the two nucleons. And you can plot this distance dependence of the potential here. Now it's complicated in a sense that there is not a single V of R function, but many. There's more than just this simple distance dependent term that you would know from, say, a Coulomb interaction. There is a dependence on the spin and isospin states of the two interacting nucleons, and that's in this representation here encoded in the coupled spin and isospin quantum numbers here. So the different lines in these plots are different combinations of the, say, spin states of the two interacting nucleons. And I use not the projection quantum numbers, which I could. I use the coupled spin S and T in capital letters here to differentiate those. The only message here is even this simple V of R term depends strongly on which spin and isospin states the two nucleons are in. And it can have this characteristic van der Waals form with a short range repulsion here and an attractive pocket at intermediate distances. Sometimes it can be purely repulsive, like this guy here for the S equals 0, T equals 0 channel. But there's more to the interaction, and you need more than these simple V of R functions. Otherwise, even the two-body physics in the form of scattering phase shifts cannot be described accurately. You need extra terms like the so-called tensor interaction S12, which is very similar to a magnetic dipole interaction, two little magnets, they have a very funny behavior if you play with the orientation and play with a relative orientation. You find that this is very much attractive and something like this or this is strongly repulsive. It's exactly the same distance to spin orientation correlation that is induced by this tensor operator. That's super important. And you have something like spin-orbit interactions that you already know from atomic physics, and you have higher order spin orbits and L squared, and each of them comes with a different distance depending. There's a question now in the chat, I'll just read it, concerning the fact that the nuclear interaction is short range. I thought naively that this would make it easier to find the structure or the shape of the potential because it puts very strong constraints on it. Then we would not have such a choice for good operator structure. Why does it make it actually more complicated? Very good question. I mean, in a sense, you could think that short range implies that you have less flexibility to play with the distance dependence, but it doesn't inhibit you from having all these complicated non-central dependencies. So sensitivity of the interaction or the force between two particles to other quantum numbers or other properties than just the distance. And this is kind of the bane and the characteristics of all nuclear interactions. There's a very strong sensitivity of the force between two nucleons on these other properties, like the spin and orbital angular momentum states the two have relative to each other, or this orientation of the spin components. So the short range, yeah, you might think it makes life easier, but remember, you are now in the regime that these super complicated extended quark-gluon objects, the nucleons overlap. So you can expect all nasty complications that symmetries allow. And that's actually what happens. You find important contributions for all of these operator structures that are allowed by symmetries. So it doesn't help you. The short range, in a sense, makes life more complicated because you are in a regime where these extended objects overlap. It's not this point charges far, far away from each other, which have a very simple interaction law between them. It's so complicated because you have overlapping complicated objects. Okay, now this is something to keep in mind. Two things of this complicated stuff here. Number one is this characteristic van der Waals shape of the central part. That's something that will show up later. And also the existence and the strength of this tensor interaction down here. We will find the importance and the consequences of that in a little while. Okay. Now, there are quite a few people from a hadron physics background, and you guys might think, okay, if we look at this as a QCD problem, why don't we solve QCD to determine this interaction between nucleons? We guys know how to solve QCD. We do lattice QCD simulations. Yes, we are very much hoping for you guys. We are very much hoping for the future, tomorrow, that at some point we are able to extract everything we need on the nucleon-nucleon interaction from lattice calculations, lattice QCD. So a real ab initio solution of QCD. There are attempts to do that since quite some time, 15 years now or so, where essentially two different schools are working on that problem. It's not so easy to extract the potential from a lattice QCD calculation of two nucleons as quark objects. One thing that you can do is you can do something like a computation of an analog to the wave function of two nucleons on ladders, and you determine the dependence on the distance from lattice calculations. You can dial in different partial waves and then kind of reverse engineer from the wave function a potential. This is an approach that is used in Japan by the HAL QCD collaboration. They are working on this since really 15 years now. It's very tough computationally. It's of course, as all the lattice computations, massive in computer requirements, and you have the difficulty to push the calculations into a regime that your quark masses become physical. They are approaching this regime, but still, as of today, the interactions extracted from such lattice calculations are simply too inaccurate to make any use of them in nuclear structure calculations. On top of that, there are some systematic problems, so you don't understand some of the mass dependencies there, which look really counterintuitive. But this is really some tough problem, and I really hope for the future that this goes forward and that one day we'll be able to use really ab initio interactions from lattice for describing nuclei. In the meantime, we do something else. In the meantime, we use the so-called chiral effective field theory. And this is an interesting story in itself, the developments, the questions here, and I will not have time to dive into that. But it is kind of the state of the art for all the ab initio calculations today. The basic idea is you go away from the elementary degrees of freedom of QCD, quarks and gluons, to effective degrees of freedom for the energy domain that you want to apply your theory to. Therefore, it's an effective field theory. And the degrees of freedom that are relevant for us are, of course, the nucleons and the pion, if you want to have it very simple. So you just build an effective theory for nucleons and pions, which respects the symmetries of QCD, and you treat all the pion physics explicitly in this effective field theory. And all the other stuff that is certainly there, which is not simple pion dynamics, that is absorbed in contact terms. So you really differentiate based on a scale separation argument, which physics you keep explicitly, that's pions, and which physics you absorb in, so to say, fudge factors or contact interactions. And these contact terms, they are for all the short range physics, all the high energy physics that's not covered by this simplistic picture of a long range pion exchange. These contact terms then come with parameters again, and these parameters have to be determined by fits to data, just as for the phenomenological older interactions as well. But you have a few really important advantages here. First of all, it's an effective field theory that comes with an ordering scheme, with a so-called power counting. Just like in a Taylor series, to put it simply, you can arrange terms and contributions to different orders, which we simply label with leading order, next to leading order, next to leading order, next to leading order, and so on. And you can simply assign individual processes or these little diagrams here to the individual orders. This ordering scheme is important because it gives you a natural kind of control mechanism which allows you to dial in the accuracy of your description that you need. You can start with a calculation in a given order, say N2LO, and if you are able to quantify your accuracy, the uncertainties, the errors, and if you decide that the error is too bad, then you can go to the next order and by that improve your description. So you have this systematicity aspect. You can always go one order higher if you find that your description is not accurate enough. That's one big advantage. And we are nowadays working with interactions at this order, so everything included up to here. And we even have the interactions that are not even on this plot anymore. So N4LO interactions are becoming available. So this is getting pretty high up in this power counting or in this expansion. And that's at least as important, once you start to discuss the two-body interaction, which is this column here, you automatically, from this theory, get multi-particle interactions predicted. You get 3 nucleon interactions, 4 nucleon interactions. They show up starting from a specific order, and they inherit many of the contact terms, the low energy constants from the two-body force. So you are able really to predict lots of the multi-particle interactions that are so important in a natural way, consistently with the two-body force. And that's really a big, big plus of this prescription. And now there's a question, do we have assurance this series converges? Excellent question. No. There are lots of discussions about the convergence behavior of this series, at least in the range that we can study explicitly. And there are also lots of discussions whether the particular ordering scheme, the specific power counting that is used here, which goes back to Weinberg, whether this is correct or whether one should look at other power countings. So therefore, this is an excellent question and it's an open question. One of the practical issues with answering this question is, whenever a new blob appears here in these plots, that means you have extra parameters to determine. So if you go higher order, you automatically increase the number of parameters that you have to fix by experimental data. And this gives you a lot of freedom. So if you're clever, then maybe this series has to converge because you build it like that by the choice of your higher order constants. So this is a bit of a tricky business, but it's really an open discussion when and how well this converges. There's another question just relating to these contact terms, low energy constants, how to determine them. Well, in the two-body sector, it's just like for the phenomenological interactions, you use simple phase shifts. So elastic scattering information. And this is something which you have in abundance at very high accuracy, and that's sufficient to fix the 25 or so constants that are present at the 2-nucleon sector. But the question is tricky if you go to the 3-nucleon forces. There are extra terms, namely these two, which don't ever appear in the 2-nucleon sector. So there are new constants, two numbers, which you have to determine somehow from 3-body systems because they only appear in the 3-nucleon forces. And this is something that is not so easy. You don't have something like 3-body scattering phase shifts. You can go for cross sections in 3-body processes or 3-body bound states. But this is an open discussion. And I'll come back to this in the very end in my last lecture. And the discussion there is exactly about these two constants, how to determine them. And it's getting worse if you go to higher orders, because then this number of constants to be determined explodes. Okay, is there a correlation between nuclear mass and the number of terms considered? I hope not, but who knows? So that's an open question. I mean, the paradigm of ab initio would be you fix your Hamiltonian once and then use it for whatever nucleus you want to. And you should never go back and change your interaction for the description of a nucleus which doesn't work out like you want it initially. But it's not clear that this pure wisdom, so this pure bottom-up approach, that means you fix all these constants in a few-body system, 2-body, 3-body, maybe 4-body here, and then go to heavier systems, whether this works out all the way to the heavy systems. That's exactly one of the key questions to be answered for the very heavy nuclei. Maybe we have to go away from this and really reconsider choice of constants if you go to heavier systems. The number of terms essentially is always what you can handle. I mean, we will always go to the highest order that we can ever manage to deal with. Yeah. Okay, one more question. May you give an intuitive interpretation of 3-nucleon interactions? Yes, I mean, this is kind of, there is a standard example why 3-nucleon interactions are to be expected. The picture you have to have in mind is we are dealing with nucleons as big extended objects that have structure themselves. And now, if you have a collection of 3 of them, then it is more than just the superposition, the sum of all the pair interaction between the 3. Because the presence of the 3rd nucleon will influence also the way the 2 others interact with each other. Therefore, this kind of effect is a genuine 3-body interaction. You cannot reduce that to sum of 2-body interactions. There is a famous example from a completely different domain, planetary dynamics. So if you look at the Earth, Moon, Sun system, all of these are extended objects. And the moon has some kind of polarization effect on the Earth, namely tides, tidal bulges. It deforms a water body on Earth. And if the sun is also in the game, this has an additional effect on this tidal deformation. And therefore, you cannot describe at precision the Earth-Moon system without considering the sun. And the sun enters, in a sense, as a three-body force term if you start to describe moon, sun, Earth as structureless particles, just like we do it here. It's extended objects which can be deformed, which can have structural changes because of the interactions. And if you boil this down to an interaction of point particle, this immediately requires multi-body forces to be captured. So this is kind of a simple picture, but it's really all rooted in this idea. These are big and complicated objects that polarize each other. Okay, so I'm running a little bit out of time. Let me just finish with one simple picture, which we'll discuss at more detail in the next lecture. So as I told you that I'm not able for many of these chiral interactions to plot the simple potential as function of distance anymore. It's not possible because these interactions are by construction what we call non-local. They cannot be represented by the simple V of R functions. You would need something like a V of R, R prime. And this is something which is absolutely non-intuitive. So don't even try it. And from now on, we'll never see these potentials again. The thing we work with and the thing we use in our many-body calculations are always something we call in slang terms partial wave matrix elements, something like this. And now it's getting messy, and I'll discuss more in detail what this all means next time. You have this two-body interaction operator in the middle here, and then two-body states on the left and on the right. And these states have lots of quantum numbers, and that's part of the magic that we'll discuss next time. These are now formulated with respect to the relative momentum of the two interacting nucleons. That's this little q. And that's just a scalar because all the rest, the angular dependence is absorbed into this angular momentum quantum number L, and then you have spin and again coupling to total relative angular momentum J in this two-particle system and the isospin part. So we like to work with these matrix elements with lots of quantum numbers in there. The reason for that is, again, computational efficiency or data reduction, compression, lossless. And that's what I'm going to discuss next time. But whenever we talk about an interaction or want to visualize an interaction, we often look at such matrix elements. And this is now for this Argon V18 potential. I fix all these other quantum numbers by selecting a so-called partial wave. That includes information on the total J, the L of bra and cat state, the S and the T. Nothing here depends on M because it's spherical symmetry, rotational symmetry, so the orientation doesn't matter. There is a very slight dependence on MT, which I ignore for here, so this is just all MT equals 0. And what you see here now is the residual freedom, this Q and Q prime. So it's the relative momentum in the bra and cat state. And this spans, if you like, a little plane, or the matrix elements are really matrices in a continuous sense. And you can plot the matrix element as function of this incoming and outgoing, if you use a different language, momentum. And this plot has nothing to do anymore with this short-range repulsion attractive pocket at the first glance, but you can connect to that. The short-range repulsion is something which is responsible for these huge contributions far off diagonal that connects a low momentum state on the bra side, for example, here on my axis, with a high momentum state on the cat side. So there's a large matrix element here between these two states. So it's a coupling between low momentum and high momentum. And this is something that's characteristic for this short-range repulsion in the interaction. And this is also there in the chiral forces. This is one example of a chiral to nucleon interaction, but you see immediately it looks very different. I mean, there's also something out here, this blob, but in this little attractive pocket here, it's completely different. And out here, it's completely different. This is all freedom, which is in the construction of these interactions. Nothing is unique here. You have constraints from data, phase shifts, you have constraints from symmetries, but there's a lot of freedom left, which is not constrained by either of the two. And therefore, there are many, many different possible interactions. There's not one unique nuclear interaction that we are going to use. Also, if you limit yourself just to the chiral domain, there are many different choices. And this is something that we have to keep an eye on. And on the page here, I just gave you a shopping list of chiral interactions that are being used nowadays. The only message here is this is not a unique procedure to determine or fix such an interaction. There are lots of choices also at a technical level. And we are just about learning what the good choices are, where the problems are, and how to better constrain this wealth of choices, what information can be used to, say, narrow down the selection of precise interactions for nuclear structure studies. So keep that in mind. There's not a unique interaction, and to be unbiased, none of them is better than the other if you talk about different chiral interactions. Okay. So I think I'm out of time here, so I will stop. There's a little bit I've left over for next time, but that's no problem. I'll shift that into the second lecture and rather ask for more questions.